Hi, we're Group 7, and we're going to be looking at the impact that BMI, age, number of children, gender, smoking habits, and region has on medical charges. Looking at background information from previous studies, these studies showed that adults aged 54 to 69 had medical costs that were twice as high if their BMI was greater than 40. And then once adults reach an age of 50, they have an exponential growth of their healthcare charges. This is shown in elderly patients whose medical charges are about 4 to 5 times the cost of teenagers. It showed that women tend to use more services and spend more on healthcare than men. This is shown prominently in middle-aged patients between 45 and 64. Smoking status is known to have a large economic burden in the United States. This makes up about $240 billion on healthcare each year. It is known that the number of children on an insurance plan increase the monthly payments as they charge for the number of dependents. And it is known that regions have an impact on the U.S. healthcare spending due to differences in the healthcare resources provided. One downside to all these studies, however, is that they study these variables independently. We are going to be looking at studying these variables and how they interact together.
In this slide, we've added some of the previous findings from previous researches and also some of the justification for the predictors that we will be using in our analysis. All three variables, BMI, age, and number of children, are continuous variables.
And to continue, we again have categorical variables that were justified by our previous research, those being gender, region, and the smoking status of the policyholder.
The variable table is given below. For age, it indicates X1, for gender, X2, BMI, X3, number of children, X4, smoking status, X5, region, X6, and then charges, response variable, which is Y.
The overall goal of the study is to determine how characteristics such as age, gender, BMI, smoking habits, number of children, and region affect healthcare costs and insurance charges for policyholders.
For our first research question, we asked, does the region lived in or the amount of children had by the policyholder have an impact on the predictive positive factor, in this case the BMI for the policyholder's charges? Here we have the initial model summary as well as the ANOVA table for the model in the form beta 0, beta 4, x4, beta 3, x3, beta 6, x6, as well as the interaction effect between beta x3, x4, and beta x3, x6. Things to note is that the p-values are extraordinarily low, and as well as the r-square, which indicates that it is a low prediction power in terms of explaining the variation of y from the variable selected. Next, we checked our assumptions for the data, the first of which being linearity through the use of an added variable plot. Most of the variables that we see here do tend to have rather linear relationships, which isn't too surprising considering the fact that they are factor levels and we're investigating what sort of effect. Some things to note, however, is that we do tend to see a slight decrease between factor 2, the amount of children between 1 and 3, and then it increases again between 4 and 5, as well as x3, the region lived in, showing a potential difference between the north and the south. Next, we checked the dataset's normality of residuals, and this was done through a Shapiro test and then a QQ plot. From the QQ plot, we can see there's just wide variation from the expected values. It's way far off the QQ line, and then the Shapiro test also confirms this with a p-value approximately at 0. Our last two assumptions that were checked in this dataset were multicollinearity and constant variance. In terms of constant variance, a Brown-Forsyth test was used, and this resulted in showing that there was a non-constant variance. P-value was well below the accepted 0.05. And the issue with multicollinearity is not exactly an issue in this because there's only one continuous variable. The rest were categorical. Children was made categorical. In this case, there's no reason that the variance expressed in one would be possibly due to multicollinearity. Because this research question involved an investigatory model rather than a predictive model, I felt it was best that we not exclude any of the variables, especially because we are looking at terms of the interaction effect between the variables, and excluding one of these might get rid of some data or some combination of factors that might just be rare in this sense. Next, we try to improve the MLR model through outlier resolution. As you can see from the influence plot and the Cook's distance plot, there are wide variety of outliers, and then this will also be continued on the next plot, which is the DF betas. So from the rather large DF beta plot, we can see that there are extraordinary amounts of outliers. However, similar to the best subset selection, if we remove these outliers, we might be removing key data points that we might not see otherwise, such as different combinations of factors, and people having insurance charges that are not considered average could be indicative of something that might need to be considered in the model. Therefore, while it might be in our best interest to remove the outliers to increase the predictive power, it does not accurately represent the data that we've collected. This issue with the outliers can also be seen in the robust regression model, which was used as sort of like a thought experiment to see how well this would reduce it. And as you can see from sort of some of the betas that we showed is that the OLS and the robust model, they both varied extraordinarily in terms of what numbers they were reducing. And we also saw a decrease in the magnitude of the interaction effects. And this led us to believe that the RLM model was not the best use for this data. Next, a weighted least squares model was taken in order to reduce the unequal variance, but this resulted again in similarly a not as usable model. And the main thing to note here was that the R-squared value, while it did increase, it didn't increase significantly enough to warrant the predictive use of it. It went from 0.042 to 0.09 after using the WLS model. One thing to note is that in an attempt to sort of see if bootstrapping could resolve some of these issues, a lot of the bootstraps that were done in terms of this model, possibly due to the fact that there was at least 9 factor levels, were inconclusive. The ones that we did see often gave nonsensical data, such as a beta n interval, and we have those shown on screen right now. Overall, I believe that bootstrapping wasn't particularly usable in solving a lot of the issues that this model sees as a predictive model. In terms of research question 1, our conclusion is from the model generated, there is not sufficient evidence to say there's an interaction effect either between children and BMI or region and BMI, suggesting the charges based on a person's BMI is not influenced by the area that they live in or by the amount of children they have. This is supported by the ANOVA and the summary of the OLS model and their remedial models having sufficiently large p-values to suggest that when using a predictive model, there is not enough evidence at each factor level that it would differentiate from the baseline of 0 children and living in the northwestern US.
The second hypothesis is on whether the age of a primary beneficiary has the same impact on insurance costs regardless of the insurance contractor's gender. The figure above shows the model summary and ANOVA output for the full model, where x1 is the age variable, x2 is the sex variable, and it is equal to 0 if female and 1 if male. And from the model summary output, we can tell that the initial model is significant in predicting insurance charges with a p-value of less than 0.05. However, from the ANOVA output, we can see that while the variables age and sex are significant in predicting insurance charges, with a p-value of less than 0.05, age times sex has a p-value of larger than 0.05, and we can conclude that it is insignificant. First, to test if age has the same impact on insurance charge in females and male, we use the GLT-F test. And here for null hypothesis, we set beta 1, 2 equals to 0. The figure above shows the ANOVA output for the GLT test. And since the p-value of 0.9349 is larger than the significance level of 0.05, we do not reject the null hypothesis. And we can conclude that age has the same impact on insurance charges regardless of gender. We use different methods of model diagnostics to test for violations of non-constant variance, normality, multicollinearity, outliers, and influential points. We use the BF test and the BP test to test for non-constant variance in the initial model. For both tests, the null hypothesis is that the model has constant variance. And the figure above shows the result of the BF and the BP test respectively. We can see that the p-value is less than 0.05, and hence we reject the null hypothesis and we conclude that there is a violation of assumption. There is non-constant variance in the initial model. And we use the Shapiro-Wilk normality test to check for violations of normality assumptions. The null hypothesis for the test is that the data is normally distributed. And we also use the normal QQ plot to visualize the distribution of the initial model. And the figure actually shows the results for the Shapiro-Wilk normality test and normal QQ plot. For Shapiro-Wilk test, we can see that the p-value is less than 0.05, and hence we reject the null hypothesis and conclude that there is a violation of the normality assumption. Moreover, we can see from the plot that the data does not follow a normality line, and hence it does not follow a normal distribution. We will use the VIF test to test for violations of multicollinearity in the initial model. However, before moving on to the result of the test, we can anticipate the model to be highly correlated with one of the variables being x1 times x2. And as a rule of thumb, VIF value larger than 10 would indicate excessive multicollinearity. And from the result above, we can conclude that all 3 variables are not excessively correlated. However, as we discussed earlier, anticipation, the VIF value for age sex variable is close to 10. We will use Cook's distance plot, hit matrix, studentized deleted residuals, DF betas to test for outliers and influential points. From Cook's distance plot, hit matrix, studentized deleted residuals, and DF betas, there appear to be no influential points. From the model diagnostics, we can conclude that there is non-constant variance, data does not follow a normal distribution, there is no excessive multicollinearity, but VIF for the third variable is very close to 10. And there is no evident outlier or influential point. To select the best model, we will be using the best subset method and stepwise method. From the figure above, we can see that model 2 and 3 are similar in the count of optimal values of SSCP, R-square adjusted CP, AICP, SBCP, and PRESS-P. This would be similar because of the subvariable, and it is a combination of x1 and x2. However, we will need the third variable to test our initial hypothesis. Hence, we will conclude that the best model is model 3. And from the figure, we can see that the best outcome from the stepwise function is the second model. However, again, the third variable is very necessary for the initial hypothesis, hence we will still keep the variable. However, aside from studying the relationship between age and sex, it is not recommended that we keep the third variable. We will be using the WLS to fix the issue of non-constant variance and robust regression for the issue of outliers. We will also use the bootstrap method to create new confidence intervals. Here we can see the model summary for the WLS model, and after using the WLS remedial measure, the BP test output is shown and now has a p-value of 1, when the null hypothesis was model has constant variance. And since the p-value is larger than 0.05, we do not reject the null hypothesis and can conclude that the model finally has constant variance after WLS remedial. The new bootstrap confidence interval is also shown in the table. Next, we will be using the robust regression method to deal with the violation of assumptions on outliers and influential points. The figure shows the model summary output for the robust regression, and we also have a new confidence interval with the bootstrap method. We can conclude that the second hypothesis, whether age has the same impact on insurance charges regardless of the gender, is correct. We have seen from the GLTF test that the p-value is larger than 0.05. Hence, we would not reject the null hypothesis and conclude that the age has the same impact on charges regardless of the gender.
The third research question is, do BMI, age, and number of children have a significant linear impact on total charges? The first step in assessing the research question is diagnostics. First is the BP and BF test, which tests if there is constant or non-constant variances. Since the p-values are less than 0.05, we reject the null and there is an issue of non-constant variances. The Shapiro-Willich normality test tests if the data is normal or not normal. Since the p-value is less than 0.05, there is a violation of normality. VIF tests if there's an issue of multicollinearity. If the predictors have a value greater than 10, then there is an issue, but since our predictors have a value of 1, there is no issue of multicollinearity. The AV plots show that there is no issue of linearity, and the first order of BMI, age, and children are sufficient on the model. Cook's distance graph is given above, and the 20th percentile and the 50th percentile are given, and it shows that there are no influential points. There are no influential cases seen on the BF beta plots. There are, however, outliers present in the box plot, and there are outliers on X due to the hat matrix, and outliers on Y from the studentized deleted residuals. The next step for the research question is model selection. 6 out of the 7 tests pick Model 3, which is charges in response to BMI plus age plus children. This can also be validated with K-folds cross-validation, as that model has the lowest RMSE value. This can also be validated with the stepwise function, picking this model because it has the lowest AIC value. The next step for the model is the remedies. WLS helps to fix the non-constant variance error. The confidence interval can be given by using the estimated betas plus or minus the standard error, and above this is the bootstrapping confidence interval. For robust, it helps fix the error of outliers, and the confidence interval can also be achieved by using the estimated betas plus or minus the standard error, and above this is the bootstrapping confidence intervals. The OLS model is also given, and the confidence intervals can be achieved by using the estimated betas plus or minus the standard error, and the bootstrapping confidence intervals are included as well. In conclusion, from the ANOVA table with the selected model, charges in response to BMI plus age in children, we can reject the null hypothesis. BMI, age, and children have a significant linear impact on the total medical charges. This means that at least one of the predictors is useful in predicting charges since all the p-values are less than 0.05. From the summary table, as BMI increases, as children increases, and age increases, the mean value of charges also increases.
Our fourth research question is looking to see if age, BMI, and smoking habits have a significant impact on medical charges. To begin, we look to see if the data has constant variance. To do this, a Brown-Forsyth test is ran, and because the p-value is less than 0.05, we conclude that the data is non-constant variance. And then we look to see if the data is normally distributed. We run a Shapiro-Wilk test for this, and we reject the null hypothesis and say that the data is non-normal. We next run a VIF test to see if there is any multicollinearity problems, and because all of the results are less than 10, we can conclude that there is no multicollinearity issue. We then look at added variable plots to see if each variable has a significant impact and if it follows a linear trend, and based on this graph we can conclude that it does. Next, we determine if there are any influential points. To do this, we first look at DF betas plots, and we just see that there are no points over 1 in magnitude, so we conclude that there are no influential points. Then we look at the influence plot in the top right, and because there's one value over 4.13 in the stud res column and 3 values over 0.006 in the hat column, there is an outlier problem in the dataset. To pick our model, the best sub algorithm is ran. This algorithm chooses the model with the best SSEP, R-squared adjusted, CP, AICP, SBCP, and PRESP. These two models are shown below. To pick from these two models, a K-fold cross-validation is ran with n equal to 10, and the best model is chosen based on the RMSE. This model is highlighted and shown here. To fix the non-constant variance issue, a WLS model was created. Its summary is shown here on the left, and the bootstrapped confidence interval for each of the betas is shown in the top left. Then to fix the outliers issue, a robust model was created. Its model summary is shown on the right, and its bootstrapped beta value confidence intervals is shown in the top right. And then finally, the OLS model is also bootstrapped, and the beta value confidence intervals are shown in the middle. From the model that we previously explained, we can conclude that age, smoking habits, and BMI while being a smoker all have a linear impact on medical charges. We found that BMI has a positive impact on medical charges when they are a smoker, smoking habits has a negative impact on medical charges in general, and age has a positive impact on medical charges.
For our research question 5, it says, Does the relationship between BMI and medical charges differ for male and female insurance beneficiaries after controlling for age, smoking status, number of children covered, and region? This is a bivariate multiple regression question, and therefore I built two models. Model 1 on BMI, holding other factors like age in smokers, children, and region constant, and model 2 as charges being the dependent variable, holding other variables also constant. So we test for linearity here using the first model, and this is the partial plot of the first model. This is the output for the first model, which shows a multiple R squared of 0.09, an MSE of 5.18, and a p-value which is not really significant. The ANOVA table also supports the claim that this first model really is not significant. For the second model, we also apply the partial plots to see the linearity, and it shows a much greater linearity with the covariates. The output here showed something strange, where we get to know that the residual standard error is really higher than that of model 1, and as we all know that a model which has a smaller MSE is far better than a model which is having a large MSE. So based on what we've done, we can say that the relationship between BMI and the sex shows a smaller change in BMI when a male is present, given a female. So this model gives smaller standard error value compared to the model relationship between the charges or medical charges and male or female, even though it gives a higher value for the coefficients. So for model diagnosis, the Shapiro test is done and a QQ plot is also performed, and it indicates that the residue in the data set for the model are not normally distributed. So the Buch-Pagan test for the first model shows that there is no constant variance among the error terms, and the VIF also shows that there is no multicollinearity amongst the covariates. The Shapiro test is done for the second model, and a QQ plot is also done for the second model, and as you can see, the QQ plot is very different. Again, in the second model, where charges is the dependent variable, we see that the errors are not normally distributed, as well as there's no constant variance in the model. If that was the situation, we use 3 tests to check for outliers. We use the DFID test, the Cook's distance test, and the DF betas to check for outliers. So what you see here is that the plot shows that there are no influential points on the estimate of the parameters. The Cook distance plot for the first model goes to show that it indicates that the value lies in the interval of 0 and 0.05, indicating that there is no influence issues on all the fitted values. This is the results for the DFID values for the first model. The output from this shows that the DFID values are greater than the threshold. Hence, you can conclude that there is a small influence on a single fitted value. For the second model, as shown here, the DF beta plots shows that the beta values are less than, and hence there are no influential points. And as you can see for the Cook's distance plot for the second model, it shows that there is no influence on all the fitted values for the covariates. This is the DFID value for the model 2. In the case of the model 2, we see that the values here, some parts are greater than the threshold value of 0.189. So it goes to show that there is an influence on single fitted values in the data for the model in which charges is a dependent variable. So for remedial measures, a weighted least square was performed, and it shows the results here. ANOVA for the weighted least square is also shown here, and there's a bootstrapping of the confidence intervals for the parameters as well for the first model. There's also a robust regression done for the first model with the output here. You see the residual standard error as 5.91 with a degree of freedom of 1,302. Again, you see a robust regression for the first model here with the bootstrapping confidence interval as well. So for this research question, which seeks to check whether the relationship between body mass index and medical charges differ for male and female insurance beneficiaries, the results indicate that indeed there is a significant difference in the two models for predicting the categorical variable sex, which is male and female. So the analysis done here indicates that among the two fitted models, the body mass index predicts male and female insurance beneficiaries better than the medical charges when all the other variables are held constant in the model.
In conclusion, our various group members went through all of their different research questions, and here's a representation of the findings as well as our concluding thoughts. So, in conclusion, our analysis of the 5 research questions shows that BMI, age, number of children, smoking status has significant linear impact on medical charges. Gender does not have a significant impact on medical charges when age is controlled. Also, our analysis found there is no significant interaction effect between region and BMI or the number of children BMI. Overall, with these conclusions, the information can be used to inform insurance companies and individuals about the factors that attribute to healthcare costs and insurance charges. Here are our references for our data set as well as our previous research and the research into the justification for all of the variables.
Thank you for watching. If you have any questions, please feel free to reach out to us.